Right. So we are going to discuss about enthalpy of atomization. The topic that we are discussing today is the continuation of D block element. So what is atomization basically? In D block, listen, you know very well, in D block all elements are metals. Okay, so the last class I forgot to say this. In D block all elements are metals. Students, observe carefully, this is very important. In D block all elements are metals. Similarly, in S block all elements are metals. Similarly, in F block most of the elements are metals and few are radioactive. Okay. In P block some are metals, some are non-metals, and very few elements are also non-metalloids. So P block has all the three category: metal, non-metal, as well as metalloid. Whereas as far as D block is concerned, all elements in D block are metals. Okay, so keep this point in mind. Therefore, in the metallic state, right, all except mercury, you know very well, except mercury, all D block elements are solids, and they have some they have definite crystal structure. Clear? So you take a solid metal, heat it. Okay, heat the metal. On heating the metal to high temperature, what will happen? The metal first become liquid, then it gets vaporized. Convert the metal, solid metal, into metal atoms in the gaseous state. In the gaseous state, you will be having individual metal atoms. In the solid state, metal atoms, okay, exist in metallic bonding. Okay, they form metallic bonding so that it will look like a cluster. Whereas on heating the metal in the solid state, if you heat it, if you go to a very high temperature, metal will first melt, then it will go to the gaseous state. Conversion of solid metal into the gaseous metal atoms is what we call as atomization. We are producing atoms, correct? Okay, from the solid metal we are producing metal atoms. So in the case of metals, this process is what we call as atomization. And the amount of heat that is absorbed here, okay, since heat is absorbed, we say that the delta H is positive here, and delta HA means enthalpy of atomization. Enthalpy of atomization, okay, is a positive quantity in the case of metals, because to produce metal, heat is absorbed. Okay, it's the first point you should keep in mind. Now, listen carefully. The amount of heat required, is this same for all metal? Is this same for all metal? Definitely not. Why? Some metals in the solid state, they have strong metallic bonding. So if you want to bring those metals to the atomic state, okay, you need to supply more heat. So enthalpy of atomization will be more. So enthalpy of atomization is directly proportional to strength of metallic bonding. If metallic bonding is strong, then convert that metal from solid state to gaseous state require high energy. So you have to supply more heat. Clear? So keep this point in mind. Enthalpy of atomization is directly proportional to strength of metallic bonding. Right? Then, if you compare enthalpy of atomization for the 4D series and 5D series with the 3D series, 4D, 5D series elements have high enthalpy of atomization because their metallic bonding are strong. So if you compare 3D, 4D, 5D, 3D series elements, okay, the metallic bonding is comparatively weak. Whereas 4D and 5D, they have a strong metallic bonding. So enthalpy of atomization for 4D and 5D series elements are generally very high compared to 3D series. Clear? See here, in 3D series, I have taken 3D series because as far as your level is concerned, 3D series is sufficient, right? If you plot standard enthalpy of atomization versus atomic number, this is atomic number, okay, Z is the symbol for atomic number. What will happen, students? You know very well, in 3D series, when you move from scandium to chromium, number of unpaired electron increases, therefore metallic bonding increases. Clear? So in 3D series, the metal which is having strong metallic bonding is chromium. So chromium has the highest enthalpy of atomization. Students, observe carefully. Chromium has highest enthalpy of atomization because chromium has maximum number of unpaired electron. You know very well, last class we discussed that. Chromium metal has 6 unpaired electron. So it has high enthalpy of atomization. Then after chromium, there is a sudden drop in the enthalpy of atomization for manganese. The question is, why enthalpy of atomization, okay, is low for manganese compared to chromium? Enthalpy of atomization is low for manganese compared to chromium. What is the reason? The reason is that typical metallic bonding, or you can say it the other way, the electronic configuration of manganese is 3d5 4s2. Students, observe carefully. 3d5 means half filled, highly stable. S2 4s2, S2 means fully filled, that is also stable. So Mn manganese atom has stable configuration. It has stable configuration, therefore the electrons, the d electrons, the 5 electron present in d subshell, okay, are reluctant to participate in metallic bonding. Okay, the tendency to form metallic bonding is less, weak. Therefore, metallic bonding is weak compared to chromium. What is the reason? The reason is they have stable electronic configuration. Okay, due to stable electronic configuration, the involvement of electrons in metallic bonding is less. The tendency to involve in metallic bonding is less. Therefore, metallic bonding is somewhat weak compared to chromium. So, since metallic bonding is weak, enthalpy of atomization or converting solid metal to gaseous metal atom is easier. So enthalpy of atomization decreases suddenly. After that, it keeps on increasing, right? And after copper, there is a sudden drop. You may ask a question: why zinc has the lowest enthalpy of atomization, right? In 3D series. Okay, so take down why manganese, zinc, why does zinc, right, has lowest enthalpy of atomization, right, in 3D series, right? What is the reason? The reason is zinc electronic configuration is 3d10 4s2. Students, observe carefully. 3d10 4s2. D subshell is completely filled. So this is very stable configuration. In stable configuration, the electrons are not involved, and there is no unpaired electron. You can say in the other way, there is no unpaired electron. So metallic bonding is very weak. I told you in the last class, zinc is an example for soft metal. Zinc, cadmium, mercury, these are all soft metals. So the involvement of the electrons in d subshell in metallic bonding is very comparatively low, very low. So metallic bonding is weak in zinc. Okay, we have weak metallic bonding. Note down this, very important, student. Zinc has weak metallic bonding, therefore enthalpy of atomization is lowest. That's the reason. Because when metallic bonding is weak, it is very easy to convert it is very easy to convert metal into yeah, it is very easy to convert metal into metal atoms. Okay, from solid to gaseous state. Is this clear, student? Any doubt?
Clear, sir.
Okay, good. Now, so this is regarding enthalpy of atomization, right? Now let me go to the next property. The next important property is about ionization enthalpy. This is another important one we should keep in mind. Okay, ionization enthalpy, also called ionization energy. Okay, ionization enthalpy, or we can also call it as ionization energy. Ionization energy. Okay, yeah, right, students. What is meant by ionization? Okay, converting a neutral atom into ion, right? In the case of D block, you know very well, all D block elements are metals, so they ready to form positive oxidation states, or they are ready to donate electron. They are metals. You know very well, in general, metals have the tendency to donate electron. Okay, so if you supply some amount of energy to the metal, suppose you take a metal atom in the gaseous state. These are all individual metal atoms, student. It is not metallic bonding. There is no metallic bonding here. Keep this in mind. These are all individual metal atoms. So, metal atom in the gaseous state, if you supply some energy, you can remove one electron. The amount of energy required to remove one electron from the neutral gaseous atom is what we call as first ionization energy. That's why I put number 1 here. Number 1 indicate first ionization energy. So you will get a monopositive ion in the gaseous state. If you remove one more electron from this monopositive ion, you need to supply more energy. So the energy required to remove one more electron from the monopositive ion is what we call the second ionization energy. After removing one electron, you will get a dipositive ion. So here, by supplying energy, we can remove one electron. By supplying again energy here, you can remove another electron. So by keep on removing electron, for the removal of electron, you need to supply energy. Those energies are called ionization energy. What is first ionization energy? Energy required to remove electron from the neutral atom. What is second ionization energy? Energy required to remove an electron from the monopositive ion. What is third ionization energy? Energy required to remove electron from the dipositive ion. Like that it goes. Okay, that's the meaning for ionization energy. Ionization energy means energy required to remove an electron from the neutral species. Okay, that is called first ionization energy. For second ionization energy, third ionization energy, we can define in a similar manner. Good. And listen, student, for a given element, for a given metal, if you compare first ionization energy, second ionization energy, third ionization energy, and so on, right? Always remember, student, second ionization energy value for a given metal is greater compared to first, and third ionization energy is greater compared to second. Like that it goes. Okay, in a given metal, if you want to remove a electron further and further and further, okay, you have to supply more and more energy. Okay, so this is a general trend. Keep this in mind. Okay. Now what I'm going to do, I'm going to focus on D block now. Listen, student, before going to see D block, I'll give the general comparison. If you compare first ionization energy of S block, D block, and P block, D block elements have a first ionization energy which is in between S and P. Because when you move from left to right, what will happen? Size decreases, effective nuclear charge increases. Okay, effective nuclear charge increases. Okay, so students, observe this carefully. First ionization, in general, ionization energy is directly proportional to effective nuclear charge of the atom. If effective nuclear charge increases, ionization energy increases. Clear? Ionization energy is inversely proportional to size. If size increases, ionization energy will decrease. Right? These are all some essential points you should keep in mind. And ionization energy is inversely proportional to screening effect. Screening effect. Okay, if there is more screening, ionization energy will decrease. These are all general information, keep this in mind. Now, listen carefully, student. In a particular series of D block, particular series means it may be 3D series or maybe 4D series or maybe 5D series, right? So particular series means it may be 3D series or 4D series or 5D series, whatever it is. In a particular series, if you move from left to right, students observe carefully, in a particular series, if you move from left to right, first ionization energy gradually increases. Gradually increases with some irregularities. It is not increasing continuously. There may be some irregularities, but in general it will increase. Keep this point in mind. In a particular series of D block, whether it is 3D series or 4D or 5D, when you move from left to right, first ionization energy increases gradually. Okay, I'm sorry. I have given here, no, sorry, right. Increases gradually with some irregularities. Okay. Now, students observe carefully. This is another important point you should keep in mind. So, in D block, when you move from left to right, first ionization energy increases in general. Why? Because size decreases. You know very well, size decreases, therefore ionization energy increases. But you know very well, the increase of size is not uniform. Okay, we have seen that in the last class. Then, next important point. What about zinc, cadmium, mercury? Zinc is the last element of 3D series. Cadmium is the last element of 4D series. And mercury is the last element of 5D series. Zinc, cadmium, mercury have abnormally high first ionization energy. Why? Due to greater stability of fully filled configuration. Say for example, if you take zinc, let me write here. See student, why in 3D series, why zinc has highest ionization energy? Zinc has, right, highest ionization energy. What's the reason? Highest first ionization energy. Why? The reason is the electronic configuration of zinc is 3D10 4s2. D10 means fully filled. S2 also fully filled. So you have very stable configuration. Stable configuration. The atom has stable configuration. Whenever atom has stable configuration, removal of electron is very, very difficult. So zinc has stable electronic configuration. Because of this reason, okay, the first ionization energy, that is removal of electron from the neutral zinc atom, is very difficult. That is the reason why zinc has highest first ionization energy in 3D series. In a similar manner, okay, in 4D series, cadmium has highest ionization energy because the electronic configuration is 4D10 5s2, fully filled. Mercury 5D10 6s2, fully filled. So due to fully filled configuration, okay, the first ionization energy of these metals, okay, is very, very high, abnormally high. Good. Now, yes, try to answer these questions. Ionization energy of manganese is greater than ionization energy of chromium. Okay, what is the reason? I'll give reason. First ionization energy of manganese is greater than the first ionization energy of chromium. Okay, give reason. It's very simple. Listen, if you want to compare, sometimes they'll ask questions like this. Okay, student, one more information. Listen, student. Student, listen, in D block. Students, observe carefully. In D block, you take a metal atom in the neutral state. It may have configuration like 3D or n minus 1D. Okay, suppose if we take 3D series, very specifically 3D series, I'll just show with 3D series. Same thing is applicable for 4D and 5D also. We have a metal atom. Students, observe carefully. Suppose it has some configuration. It has some number of electron in D and some number of electron in S. Okay. Just for understanding purpose, I'll take one example. Say I'll take vanadium. Vanadium, the electronic configuration for vanadium is 3d3 4s2. Students, observe carefully. In 3d3 4s2. What happens if I remove one electron? If I remove one electron, I'll get vanadium plus ion plus 1. Students, listen. In neutral vanadium, students, observe carefully. We have 3d subshell having 5 orbitals. Okay, this is energy of the 3d subshell, and this is energy of the 4s. Observe carefully, student. 4s. Right? So energy of the 3d, energy of the 4s, they are very close in the neutral metal atom. I'm sorry, I made a mistake. And here we have 3 electrons. Okay, 1, 2, 3. Vanadium has 3 electron in d subshell and 2 electron in s subshell. Okay. What happens if I remove one electron? If I remove one electron, the energy gap increases, student. Energy gap increases. We have removed one electron, therefore we have 3 electron in d subshell, and now we have only 1 electron in 4s. But since the gap is large, that 1 electron also will enter in 3d subshell. Okay, because the energy gap increases. Right? Therefore, the electron prefers to occupy lower energy level. Right? So, the expected configuration is 3d3 4s1. That doesn't occur. Right? What actually observed is 3d4. Why 3d4? Because when we remove one electron, you will get vanadium positive ion. In this positive ion, the energy of the 3d and 4s gap increases. Because of that, the electron present in 4s, it prefers to occupy the lower energy level. Okay, therefore the electronic configuration becomes 3d4. Is this clear, student? Students, is this clear? Keep this point in mind. Based on this, they will ask question like this, students. This is very important question for IIT main examination. If you go for IIT main, it's very important. Listen, student. They will ask question like how many unpaired electrons? Find the number of unpaired electrons. Number of unpaired electrons in ion Fe plus 1. Find the number of unpaired electron in Fe plus 1. This is the question. Normally, most student will commit mistake here, student. Listen. In the case of ion, the electronic configuration is 3d6 4s2. Students, observe carefully. 3d6 4s2. Right? This is fully filled. Don't worry about this. In d6, you know, d subshell has 5 orbital, and we have 6 electrons here. So 1, 2, 3, 4, 5, 6, and here we have 4 unpaired electrons. Right? In neutral ion atom, we have 4 unpaired electrons. When you remove one electron, you will get Fe plus 1. Fe plus 1. We are removing electron from s subshell, so you will get 3d6 4s1. This is expected. What normally students will say, listen, what normally student will say, d subshell has 6 electron, so we have 4 unpaired electron here. S subshell has 1 electron, we have 1 electron. Therefore, they say that there are 5 unpaired electrons. But this is wrong. Why? Once you remove electron, you will get ion in plus 1. In ion plus 1 state, the energy gap between 3d and 4s will increase. So, the s electron will prefers to occupy 3d. So, the actual configuration is not 3d6, it is 3d7. 3d7 4s0 student. This is the configuration. Now we have 7 electron in the d subshell. So if you place 7 electrons in d subshell, 1 2 3 4 5 6 7. Now see how many unpaired electrons are there, student. Can you tell me how many unpaired electrons? Students, how many? Yes, there are only 3 unpaired electrons. What we expect is 5, but actually it's only 3. Right? So keep this question in
Sir,
mind.
isn't there only one unpaired electron?
Where?
Why can't the 2 electrons be paired, sir? The 5th and the 6th one.
Here, here?
Yes, sir.
We have 7 electrons, right? In d subshell we have 7 electrons. Okay. How will you fill the 7 electrons in d subshell? First you should put 1 1 1 1 electron. Make it off-filled. Once all the orbitals become off-filled, you have to pair up. No other chance, right?
Yes, sir. Yes, sir.
So the 6th electron and 7th electron get paired here. Therefore, we have only 3 unpaired electrons. Okay. What most people will do is that they'll put 5. 5 is the wrong answer. Keep this in mind. Because, one second, sorry. Because in D block, whenever you remove one electron, the energy of the 3d and 4s changes. So the configuration, okay, changes. Right? Keep this point in mind. Very, very important, student. Okay. Now, listen, student. So, keeping this point in mind, I'm going to discuss these questions. Yeah. So here the questions given are manganese and chromium. They are asking you to compare the first ionization energy. Okay. And it is given that first ionization energy of manganese is high. What is the reason? The reason is this. What is the answer? First you write the configuration of manganese. Students, observe carefully. Manganese electronic configuration is 3d5 4s2. Students, you must know the configuration of 3d series at least. You must know. Right? 3d5 4s2. Listen, student, d5 off filled, s2 fully filled, so it is a stable configuration. It is highly stable configuration. Clear? If I remove one electron, to remove one electron from this, you require more energy. Okay, you require more energy. Right? So ionization energy, first ionization energy for manganese is high. Why it is high? Because the new manganese atom is highly stable. They have very stable configuration. If you take chromium, the electronic configuration of chromium is 3d5 4s1. Students, observe carefully. d5 is off filled, s also off filled. This is also stable, but if you compare these two, fully filled configuration is somewhat more stable compared to off filled configuration. Students, observe carefully. Fully filled configuration is somewhat more stable compared to off filled. Therefore, this is also stable, but if you compare these two, stability is more for manganese. Therefore, if you remove electron from this, okay, if you remove one electron from this, I'll get chromium plus in 3d5 configuration. Whereas if I remove one electron here, what will I get, student? Can you tell me? If I remove one electron here, what will be the configuration? Can anyone tell me? Is it 3d5 4s1? Very good. It is not 3d5 4s1. It becomes 3d6, correct? Because energy gap increases. It becomes 3d6. Now tell me, student, after removing electron, I am getting 3d6 here. Here I am getting 3d5. Which is more stable among the two?
Cr plus.
Yeah, Cr plus is more stable. Listen, if I remove one electron, I am getting more stable. I am getting more stable ion. Therefore, chromium, removal of electron from chromium is not that difficult. Because anyway, chromium plus also stable, so you can remove easily. That is the reason why first ionization energy for chromium is low. Whereas here, if you remove an electron, I am getting 3d6. 3d6 not that stable. It's not very stable compared to this. So from stable atom, you are going to convert a stable atom into a less stable ion. It is a difficult process. Whereas here, it is stable, but if you remove electron, this is also stable. So the energy change is just little. Okay, therefore this process can occur easily. Okay, if a process can occur easily, the energy involvement is low. That's a point you should keep in mind. Okay, so first ionization energy for manganese is high, first ionization energy for chromium is low. Is this clear, student? The reason is this. In neutral atom, manganese has stable configuration, chromium also has stable configuration. This is also stable, but since this is fully filled, it is little more stable compared to this. And if you compare the product side, it is very easy. Mn plus is less stable, whereas Cr plus is more stable. Therefore, since you are producing more stable ion, the energy required is less. Here you are producing less stable ion. Less stable ion means you have to put more energy. So that's the reason why first ionization energy for manganese is high. It's difficult to remove electron from manganese. Is this clear, student?
Yes, sir.
Okay. Now, see the next question. Now I am comparing second ionization energy. If you compare second ionization energy for chromium and manganese, second ionization energy for chromium is high. What is the reason? Yeah. To compare second ionization energy, we should take chromium positive ion and manganese positive ion 1 plus. What is the electronic configuration of chromium plus 1? Yes, we saw that it is 3d5 for chromium plus 1. For Mn plus 1, the configuration is 3d6. Among the two, which is more stable, student? Among the two, which is more stable? Cr plus is more stable, right? This is more stable. More stable. Therefore, since the ion is more stable, removal of electron is difficult here. Therefore, if you convert Cr plus 1 into Cr plus 2, okay, you require more energy. So second ionization energy is high. High for chromium. Whereas this is unstable configuration. If I remove one electron, I will get Mn plus 2 with the configuration 3d5. 3d5 is stable configuration, students. Student, observe carefully. This is unstable, or this is less stable. Okay, this is less stable. Whereas if I remove one electron, I am getting stable configuration. Therefore, removal of electron is easy here. Okay, the ion itself ready to give an electron because it is less stable. By donating electron, it goes to the more stable state. Therefore, the energy required for the removal of electron from here is less. So second ionization energy is low in the case of Mn plus 1. Is this clear, student? Right? Yeah. So
Yes, sir.
listen, in general, student, observe carefully. You just see the left hand side and right hand side. If left hand side is stable, ionization energy will be high. If the right hand side species is stable, ionization energy is low. Simple. That's all. Or if the reactant is stable, ionization energy will be high. If the product is stable, ionization energy is low. Okay, keep this point in mind. Very important. Okay, now listen, student. In 3D series, this is okay. Before going to see the other one, let me give this point. Let me give this question. Yes, student, can you answer this question now? First ionization energy of copper and zinc, if you compare, first ionization energy of zinc is very high. What is the reason? For first ionization energy, you should take neutral atom, right? So what is the answer? I'll take copper. The electronic configuration of copper is 3d10 4s1. Yes, stable. Zinc, electronic configuration of zinc is 3d10 4s2. This is also stable, but this is fully filled. So compare with this, this is little more stable. Now after removal of electron, if you remove one electron here, If you remove one electron, it's called first ionization energy. Okay, the energy required for this is called first ionization energy. If you remove one electron here, what will I get? I'll get 3d10. 3d10 is stable configuration, correct? Stable. Whereas if I remove one electron here, I'll get zinc 3d10 4s1. 3d10 4s1. Okay, this is also stable. Students, observe carefully. Observe carefully. Here you are removing an electron. Okay, here also you are removing electron. Since this is highly stable, okay, don't worry about that. Since this is more stable, removal of electron is difficult. I repeat, compare the two. Okay, if you compare the electronic configuration 3d10 4s1 and 3d10 4s2, since this is fully filled configurations are little more stable compared to off-filled configuration. Therefore, the ionization energy of zinc is high. First ionization energy. Now, see the next question, student. Now I am talking about, now the question given is second ionization energy for copper and zinc. Second ionization energy means you should take the monopositive ion, right? Monopositive ion. Copper plus 1 electronic configuration is 3d10. Zinc plus 1 electronic configuration is 3d10 4s1. 3d10 4s1. Okay, if I remove one electron here, the energy required for this is called second ionization energy. I'll get Cu plus 2 configuration 3d9. If I remove one electron here, it is called second ionization energy for zinc. I'll get zinc plus 2 with the configuration of 3d10. 3d10. Students, observe carefully. If you compare the product, here d10 is fully filled, so it is stable. It is stable. So if I remove one electron, I will get stable configuration, no doubt. Whereas here, if I remove one electron from d10, I am getting less stable configuration. 3d9 is less stable. From this is more stable. D10 is more stable, right? More stable. So I am going from more stable to less stable. It is difficult. Therefore, second ionization energy for copper is high. Whereas here we are moving from this is also stable. This is also stable. This is also stable. So stable to stable, the energy involvement is not that much. Okay, even if you remove electron, this configuration remains stable. So energy required to remove the second electron is somewhat easy. Since this process is easy, second ionization energy is low. So keep this point in mind. Second ionization energy for copper is high. Is this clear, student? Students, is this point clear? Any doubt? Okay, right. Now, if you compare, right, how the first ionization energy varies in 3D series. So here I am plotting first ionization energy versus atomic number in the case of 3D series. From scandium to titanium, first ionization energy increase. I have told you in the beginning itself, ionization energy, first ionization energy increases from left to right. Yes, it is increasing, but not regularly, with some irregularity. People will ask this question, student. After titanium, first ionization energy decreases for vanadium. Why? Why vanadium has lower ionization energy compared to titanium? Okay, first ionization energy of vanadium is low. Why? Why? What's the reason? Students, observe carefully. Let me discuss this in a separate page. Students, observe this carefully. Very important point. Why first ionization energy of vanadium is low? Vanadium, what's the electronic configuration? 3d3 4s2. Students, in d subshell we have 3 electrons. D subshell we have 5 orbitals and there are 3 electrons. 1, 2, 3. All the electrons have same spin. You know very well, electrons with the same spin in a subshell can be exchanged. You can exchange this electron with this. You can exchange this electron with this. you can exchange this electron with this. So there are 3 exchanges possible. 3 exchange. Students, observe carefully. Whereas if I remove one electron from vanadium, the energy required for this process is called first ionization energy. I'll get vanadium plus 1. Can anyone tell me what's the configuration of vanadium plus 1? Is it 3d3 4s1? Very good. The configuration is 3d4. So now d subshell, students observe carefully, d subshell, it has 5 orbitals. Okay, 1 to the 5, and we have 4 unpaired electrons. 4 electrons. I'll put 4 electrons with the same spin like this. Now see, students, this electron can be exchanged with this. This electron can be exchanged with this. We can exchange these two. We can exchange this with this. We can exchange this with this. We can exchange this with this. How many exchanges possible? Here we have 3, 4, 5, 6. So 6 exchanges possible. Listen, student. More the number of exchanges possible, okay, higher is the stability. So here, due to high exchange energy, because of exchange we have exchange energy. Since exchange energy is high, stability is high. Listen, stability is one important point, student, is directly proportional to exchange energy. If you have more exchanges, exchange energy is high. If your exchange energy increases, stability will increase. Yes,
Okay, sir.
yeah. So if you remove one electron, I'll get 3d4. In 3d4, number of exchanges is more. So exchange energy is more. If exchange energy is more, stability will increase. Therefore, vanadium plus 1 is more stable. Therefore, removal of electron from vanadium is quite easy, student. If product side is stable, ionization energy is low. That is the reason why after titanium, ionization energy decreases. So first ionization energy of vanadium is low because of this reason. It's because of exchange energy. Exchange energy of vanadium plus 1 is more. Therefore, stability of vanadium plus 1 is more. Since vanadium plus 1 is more stable, it is easy to remove electron from vanadium. Okay, very simple. Why first ionization energy of cobalt decreases? Can you give explanation for this in a similar manner? Why first ionization energy of cobalt decreases? The electronic configuration of cobalt is, let me write here, 3d7 4s2. Okay, leave this s2. In d7, d subshell has 5 orbitals, 1, 2, 3, 4, 5. We have 7 electron. First put electron with the upward spin, then pair it. Okay, now we have 3 unpaired electrons, student, 3 unpaired electron. We have some exchanges possible. Okay, we have some exchanges. But if I remove one electron from cobalt, that energy is called first ionization energy. I'll get cobalt plus 1. Cobalt plus 1 configuration is 3d8. In 3d8, student, observe carefully. In 3d8, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. Now, how many exchanges possible here? Listen, student. Here also number of exchanges will increase. Listen, same spin, upward spin can be exchanged with upward spin. So 1, 2, 3, 4 I can exchange. Downward spin can be exchanged with this. Right? So listen, upward spin. Listen, student, upward spin we have 5 here. Here also we have 5. So don't worry about the upward spin. Compare the downward spin. That is the spin I represented here as downward spin. Okay, it may be clockwise, anti-clockwise, like that. Okay, downward spin, and here also we have downward spin. These 2 electrons can be exchanged. So upward spin 5, here also upward spin 5. They are equal, so don't worry about that. Take the downward spin. Okay, downward spin we have only 2 here, so only 1 exchange possible. Here this downward spin electron can be exchanged with this, and this can be exchanged with this, and this can be exchanged with this. So there are 3 possibilities. Number of exchanges increases, so cobalt plus is little stable, okay, after the removal of electron due to exchange energy. Due to the increase in exchange energy, cobalt plus 1 is little more stable compared to cobalt. Therefore, removal of electron is somewhat easy. Is this clear, student? Don't worry about the upward spin, because here also we have a 5 upward spin, here also we have 5 upward spin. Don't worry about that. Take the downward spin and see the number of exchange. Is this clear? Hello, students?
Yes, sir.
Yes, ma'am. Take note. That's the reason why after iron, the first ionization energy decreases. In 3D series, zinc has the highest first ionization energy. Why? Very stable configuration. What's the configuration? 3D10 4s2, fully filled, highly stable. So removal of electron from zinc is very tough. You need to supply more energy. That's the reason why zinc has the highest first ionization energy in 3D series. Is this clear? And remember these 2 points, very, very important. Clear, student? Is this clear?
Yes, sir.
Yeah, this is the way we explain, right, the reason for the lower ionization energy. Now, the next point, student. First ionization energy in general, if you compare 3D, 4D, 5D, listen, student, from 3D to 4D, if you move down, size increases. 3D to 4D, size increases. If size increases, ionization energy will decrease. So, if you compare 3D series element and 4D series element, 3D series element have higher ionization energy. 3D to 4D, size increases. If size increases, ionization energy will decrease. So, compared to 3D series element, 4D series element have less ionization energy. If you compare 4D and 5D, student, you have 4f electrons, right? 4f electron will come here in 5D. Lanthanide contraction will come. Because of lanthanide contraction, effective nuclear charge increases. From 4D to 5D, effective nuclear charge increases, therefore ionization energy increases. So if you compare 3D and 4D, 3D has higher ionization energy. If you compare 4D and 5D, 5D has higher ionization energy. Then what is the order? The general order is this, student. Very important, note down. 5D series element have high first ionization energy, then 3D. 1 second, it is just stuck. Yeah. 5D has high ionization energy, then 3D, then 4D. This is the general order. Keep this in mind. Is this clear, student? Is this clear?
Yes, sir.
Yeah. I'll give one example here. Just now done, student. Copper, silver, gold. Copper belongs to 3D series, silver belongs to 4D series, and gold belongs to 5D series. Okay. What will be the ionization energies, first ionization energies of these elements, or how they vary? First ionization energy versus these elements. So according to this order, remember 5D series element have high ionization energy. So first copper to silver ionization energy decreases. This is copper, this is silver. After silver, ionization energy will increase. So gold has the highest ionization energy among copper, silver, gold. Is this clear? Remember, student, this is very important point. Copper to silver ionization energy decreases. Why? See, if you write the configuration, student, observe carefully, student. Copper, electronic configuration. For copper, then for silver, the electronic configuration is 4d10 5s1. For gold, students, observe carefully, 4f14 5d10 6s1. This is electronic configuration. I introduced 4f here. Since 4f14 is there, we have lanthanide contraction. Because of lanthanide contraction, effective nuclear charge increases. So from copper to silver, size increases. From silver to gold, effective nuclear charge increases. Students, observe this carefully. Okay, if size increases, ionization energy will decrease. That's why from copper to silver, ionization energy decreases. From silver to gold, effective nuclear charge increases, so ionization energy increases. Right? So among copper, silver, gold, listen student, first ionization, if you compare, gold has the highest first ionization energy, right? Then copper, then silver. That's the reason why I gave the order 5D series, 3D series and 4D series. This is the general order. Is this clear?
Yes, sir.
Right? Note down. This is very important point. Okay? People expect this type of question in the examination. Now, let me go back here. So this is the general order, but there are some exceptions, student. Exceptions. See, if you compare scandium, yttrium, lanthanum, scandium is the first element of 3D series. Yttrium is the first element of 4D series. Lanthanum is the first element of 5D series. 5D. What is the expected order? The expected order is this. That is 5D elements supposed to have high ionization energy, then 3D scandium, then yttrium. This is the expected order, but this is not observed. Why? In lanthanum, there is no 4f electron, student. There is no 4f electron in lanthanum. There is no lanthanide contraction here. Therefore, from scandium to yttrium, size increases. Yttrium to lanthanum also size increases. There is no effective nuclear charge place here. Okay, from left to right. Actually, it's not left to right. It is top to bottom. 3D, 4D, 5D, top to bottom, size increases. Here you need not worry about effective nuclear charge. If size increases, ionization energy will decrease. So first ionization energy order is scandium, then yttrium, then lanthanum. This is the order. Student, note down, very important. Here lanthanide contraction never play. Why? In lanthanum there is no 4f electron. Clear? Is this clear? Student?
Yes, sir.
Yeah, good. Now, see, this is another important question often expected in the examination. Compare the first ionization energy of nickel, palladium, platinum. Nickel, palladium, platinum. Right? What is the normal order? See, nickel belongs to 3D series, palladium belongs to 4D series, platinum belongs to 5D. What is the expected order? Expected order is 5D supposed to have high ionization energy, so platinum supposed to have high ionization energy, then nickel, then palladium. Okay, so this is expected order. Platinum, okay, then nickel, then palladium. This is the expected order, but this is not observed. Why? The reason is, listen student, electronic configuration of nickel is 3D8 4s2. 3D8, I'll write, okay, let me write in a separate page. No problem, I'll write here. Student, nickel electronic configuration is 3D8 4s2. It's not that stable. Whereas palladium is an exception. I told you in the beginning. Last class I have told you. Palladium configuration is 4D10, student. Remember, it's not 4D8 5s2. No. Palladium configuration is 4D10. 4D10 means it is stable. Stable configuration. So removal of electron from palladium is difficult. Therefore ionization energy is high. So if you compare nickel and palladium, people normally will, what we say is nickel, they expected order. Nickel supposed to have high ionization energy, but it is wrong. Why? Palladium has stable configuration, so removal of electron from palladium is difficult. Therefore the order, the correct order is this: platinum, then palladium, then nickel. Nickel has the lowest ionization energy. This is the order, correct order. Is this point clear, student?
Yes, sir. Yes, sir.
Okay, so if you compare nickel and palladium, palladium has high ionization energy. Why? If you compare nickel and palladium, palladium has high ionization energy. Why?
Stable electronic configuration.
Stable configuration. Palladium configuration is 4d10 stable configuration. Okay, take down. Take down. Why platinum has highest among the three?
5D, sir.
This is 5d and we have high effective nuclear charge increases, correct? Because lanthanide contraction will come here, effective nuclear charge will increase. So due to high effective nuclear charge, platinum has high ionization energy among the three. Is this point clear, student? In the next class, see, nickel 2 compounds are thermodynamically more stable than platinum 2 compounds. Give reason. This type of questions are normally expected in NCERT. Nickel, platinum belong to same group. Okay, this is actually 3D series. This is also actually 5D. But nickel 2 compounds are thermodynamically more stable. Why? What's the reason? The reason is, student, nickel 2 means we have to remove 2 electrons from nickel. So first ionization energy plus second ionization energy, okay, sum of these two for nickel. Similarly, first ionization energy plus second ionization energy, sum of these two for platinum, if you compare. Okay, ionization energy is the sum of these two ionization energy is less for nickel. Therefore, it is very easy to form nickel 2 compounds. That's the reason why nickel 2 compounds are more stable, because they have low ionization energy. The sum of these two, sum of first ionization and second ionization for nickel is less compared to platinum. So nickel 2 compounds, okay, are thermodynamically more stable, easy to form. Listen, nickel, platinum to platinum 2. Listen, student. See, if it is stable, that means the removal of 2 electron will be easier, correct? Product is stable, correct? This is what given, right? Nickel 2 compounds are more stable than platinum 2 compound. What is the reason? Nickel 2 compound is more stable than platinum 2. Platinum 2 is less stable. That's the meaning, correct? Listen, after removal of electron, you are getting stable structure. That means removal of electron is easy, correct?
Yes, sir.
Therefore, sum of the two ionization energy, because you are removing 2 electron, first ionization energy and second energy, this sum is less for nickel compared to the sum of first and second ionization energy for platinum. Since it is less, so removal of electron is easy, so nickel 2 compounds readily formed. In a similar manner, see this question, nickel 4 compounds are thermodynamically less stable compared to platinum 4 compounds. Nickel 2, if you compare, okay, nickel 2, the sum of these two is low. If you compare nickel 4 with the platinum 4, students observe carefully, we have to remove 4 electron, right? So first ionization energy plus second ionization energy plus third ionization energy plus fourth ionization energy. If you add all the energies for nickel, and if you remove electron from platinum in a similar manner, first ionization energy plus second plus third plus fourth, the sum of this for platinum, if you compare, this sum is low. Sum of these 4 ionization energy is low for platinum. Therefore, platinum 4 compounds are very easy to form. So platinum 4 compounds are generally stable. We are giving the explanation based on ionization energy. Is this point clear, student? Ionization energies are available in book. If you want, you can check also. But in the examination, you just give this information is sufficient. You need not remember the data. Values not necessary, but even then the values are available in book.